Hello, welcome to the Coursera course on neural networks for machine learning. Before we get into the details of neural network learning algorithms, I want to talk a little bit about machine learning, why we need machine learning, the kinds of things we use it for, and show you some examples of what it can do. So the reason we need machine learning is that there's some problems where it's very hard to write the programs. Recognizing a three-dimensional object, for example, when it's from a novel viewpoint in new lighting conditions in a cluttered scene, is very hard to do. We don't know what program to write because we don't know how it's done in our brain. And even if we did know what program to write, it might be that it was a horrendously complicated program. Another example is detecting a fraudulent credit card transaction, where there may not be any nice simple rules that will tell you it's fraudulent. You really need to combine a very large number of not very reliable rules. And also, those rules change over time because people change the tricks they use for fraud. So we need a complicated program that combines unreliable rules and that we can change easily. The machine learning approach is to say, instead of writing each program by hand for each specific task, for a particular task we'll collect a lot of examples that specify the correct output for a given input. A machine learning algorithm then takes these examples and produces a program that does the job. The program produced by the learning algorithm may look very different from a typical handwritten program. For example, it might contain millions of numbers about how you weight different kinds of evidence. If we do it right, the program should work for new cases as well as the ones it's trained on. And if the data changes, we should be able to change the program relatively easily by retraining it on the new data. And now, massive amounts of computation are cheaper than paying someone to write a program for a specific task, so we can afford big, complicated machine learning programs to produce these task-specific systems for us. Some examples of the things that are best done by using a learning algorithm are recognizing patterns, so for example objects in real scenes, or the identities or expressions of people's faces, or spoken words. There's also recognizing anomalies. So an unusual sequence of credit card transactions would be an anomaly. Another example of an anomaly would be an unusual pattern of sensor readings in a nuclear power plant. And you wouldn't really want to have to deal with those by doing supervised learning, where you look at the ones that blow up and see what caused them to blow up. You'd really like to recognize that something funny is happening without having any supervision signal. It's just not behaving in its normal way. And then there's prediction, so typically predicting future stock prices or currency exchange rates, or predicting which movies a person will like from knowing which other movies they like and which movies a lot of other people liked. So in this course, I'm going to use a standard example for explaining a lot of the machine learning algorithms. This is done in a lot of science. In genetics, for example, a lot of genetics is done on fruit flies. And the reason is they're convenient. They breed fast, and a lot is already known about the genetics of fruit flies. The MNIST database of handwritten digits is the machine learning equivalent of fruit flies. It's publicly available. We can get machine learning algorithms to learn how to recognize these handwritten digits quite quickly, so it's easy to try lots of variations. And we know huge amounts about how well different machine learning methods do on MNIST. And in particular, the different machine learning methods were implemented by people who believed in them, so we can rely on those results. So for all those reasons, we're going to use MNIST as our standard task. Here's an example of some of the digits in MNIST. These are ones that were correctly recognized by neural net the first time it saw them. But they're ones where the neural net wasn't very confident. And you can see why. I've arranged these digits in standard scanline order, so zeros, then ones, then twos, and so on. If you look at a bunch of twos, like the ones in the green rectangle, you can see that if you knew they were a handwritten digit, you'd probably guess they were 2s. But it's very hard to say what it is that makes them 2s. There's nothing simple that they all have in common. In particular, if you try and overlay one on another, you'll see it doesn't fit. And even if you skew it a bit, it's very hard to make them overlay on each other. So a template isn't going to do the job. And in particular, a template is going to be very hard to find that'll fit those 2s in the green box and won't also fit the things in the red boxes. So that's one thing that makes recognizing handwritten digits a good task for machine learning. Now, I don't want you to think that's the only thing we can do. It's a relatively simple thing for a machine learning system to do now. And to motivate the rest of the course, I want to show you some examples of much more difficult things. So we now have neural nets with approaching 100 million parameters in them that can recognize 1,000 different object classes in 1.3 million high-resolution training images got from the web. So there was a competition in 2010, and the best system got 47% error rate if you look at its first choice, and 25% error rate if you say it got it right if it was in its top 5 choices, which isn't bad for 1,000 different objects. Jitendra Malik, who's an eminent neural net skeptic and a leading computer vision researcher, has said that this competition is a good test of whether deep neural networks can work well for object recognition. And a very deep neural network can now do considerably better than the thing that won the competition. It can get less than 40% error for its first choice and less than 20% error for its top 5 choices. I'll describe that in much more detail in lecture 5. Here's some examples of the kinds of images you have to recognize. These are images from the test set that it's never seen before. And below the examples, I'm showing you what the neural net thought the right answer was, where the length of the horizontal bar is how confident it was, and the correct answer is in red. So if you look in the middle, it correctly identified that as a snowplow, but you can see that its other choices were also fairly sensible. It does look a little bit like a drilling platform. And if you look at its third choice, a lifeboat, it actually looks very like a lifeboat. You can see the flag on the front of the boat and the bridge of the boat and the flag at the back and the high surf in the background. So its errors tell you a lot about how it's doing it, and they're very plausible errors. If you look on the left, it gets it wrong, possibly because the beak of the bird is missing and because the feathers of the bird look very like the wet fur of an otter. But it gets it in its top 5, and it does better than me. I wouldn't know if that was a quail or a ruffed grouse or a partridge. If you look on the right, it gets it completely wrong. A guillotine, you can see why it says that. You can possibly see why it says orang-utan, because of the sort of jungle-looking background and something orange in the middle, but it fails to get the right answer. It can, however, deal with a wide range of different objects. If you look on the left, I would have said microwave as my first answer. The labels aren't very systematic, so actually the correct answer there is electric range, and does get it in its top 5. In the middle, it's getting a turnstile, which is a distributed object. It can do more than just recognize compact things, and it can also deal with pictures as well as real scenes, like the bulletproof vest. And it makes some very cool errors. If you look at the image on the left, that's an earphone. It doesn't get anything like an earphone, but if you look at its 4th bet, it thinks it's an ant. And to begin with, you think that's crazy. But then if you look at it carefully, you can see it's a view from an ant from underneath. The eyes are looking down at you, and you can see the antennae behind it. It's not the kind of view of an ant you'd like to have if you were a greenfly. If you look at the one on the right, it doesn't get the right answer, but all of its answers are cylindrical objects. Another task that neural nets are now very good at is speech recognition, or at least part of a speech recognition system. So speech recognition systems have several stages. First, they pre-process the sound wave to get a vector of acoustic coefficients for each 10 milliseconds of sound wave. And so they get 100 of those vectors per second. They then take a few adjacent vectors of acoustic coefficients, and they need to place bets on which part of which phoneme is being spoken. So they look at this little window, and they say in the middle of this window, what do I think the phoneme is and which part of the phoneme is it? And a good speech recognition system will have many alternative models for a phoneme, and each model it might have 3 different parts. So it might have many thousands of alternative fragments that it thinks this might be, and you have to place bets on all those thousands of alternatives. And then once you've placed those bets, you have a decoding stage that does the best job it can of using plausible bets, but piecing them together into a sequence of bets that corresponds to the kinds of things that people say. Currently, deep neural networks pioneered by George Dahl and Abdul Rahman Mohammed at the University of Toronto are doing better than previous machine learning methods for the acoustic model, and they're now beginning to be used in practical systems. So Dahl and Mohammed developed a system that uses many layers of binary neurons to take some acoustic frames and make bets about the labels. They were doing it on a fairly small database, and they only used 183 alternative labels. And to get their system to work well, they did some pre-training, which will be described in the second half of the course. After standard post-processing, they got 20.7% error rate on a very standard benchmark, which is kind of like the MNIST for speech. The best previous result on that benchmark for speaker-independent recognition was 24.4%, and a very experienced speech researcher at Microsoft Research realized that that was a big enough improvement that probably this would change the way speech recognition systems were done, and indeed it has. So if you look at recent results from several different leading speech groups, Microsoft showed that this kind of deep neural network, when used as the acoustic model in a speech system, reduced the error rate from 27.4% to 18.5%, or alternatively, you could view it as reducing the amount of training data you needed from 2,000 hours down to 309 hours to get comparable performance. IBM, which has the best system for one of the standard speech recognition tasks for large vocabulary speech recognition, showed that even its very highly tuned system that was getting 18.8% can be beaten by one of these deep neural networks. And Google fairly recently trained a deep neural network on a large amount of speech, 5,800 hours. That was still much less than they'd trained their Gaussian mixture model on. But even with much less data, it did a lot better than the technology they had before. So it reduced the error rate from 16% to 12.3%, and the error rate is still falling. And in the latest Android, if you do voice search, it's using one of these deep neural networks in order to do very good speech recognition. In this video, I'm going to tell you a little bit about real neurons and the real brain, which provide the inspiration for the artificial neural networks that we're going to learn about in this course. In most of the course, we won't talk much about real neurons, but I wanted to give you a quick overview at the beginning. There are several different reasons to study how networks of neurons can compute things. The first is to understand how the brain actually works. You might think we could do that just by experiments on the brain, but it's very big and complicated, and it dies when you poke it around, and so we need to use computer simulations to help us understand what we're discovering in empirical studies. The second is to understand a style of parallel computation that's inspired by the fact that the brain can compute with a big parallel network of relatively slow neurons. If we can understand that style of parallel computation, we might be able to make better parallel computers. It's very different from the way computation is done on a conventional serial processor. It should be very good for things that brains are good at, like vision. And it should also be bad for things that brains are bad at, like multiplying two numbers together. A third reason, which is the relevant one for this course, is to solve practical problems by using novel learning algorithms that were inspired by the brain. These algorithms can be very useful even if they're not actually how the brain works. So in most of this course we won't talk much about how the brain actually works. It's just used as a source of inspiration to tell us that big parallel networks of neurons can compute very complicated things. I'm going to talk more in this video, though, about how the brain actually works. A typical cortical neuron has a gross physical structure that consists of a cell body and an axon where it sends messages to other neurons, and a dendritic tree where it receives messages from other neurons. Where an axon from one neuron contacts a dendritic tree of another neuron, there's a structure called a synapse, and a spike of activity travelling along the axon causes charge to be injected into the postsynaptic neuron at a synapse. A neuron generates spikes when it's received enough charge in its dendritic tree to depolarize a part of the cell body called the axon hillock. And when that gets depolarized, the neuron sends a spike out along its axon. And the spike's just a wave of depolarization that travels along the axon. Synapses themselves have interesting structure. They contain little vesicles of transmitter chemical, and when a spike arrives in the axon, it causes these vesicles to migrate to the surface and be released into the synaptic cleft. There's several different kinds of transmitter chemical. There's ones that implement positive weights and ones that implement negative weights. The transmitter molecules diffuse across the synaptic cleft and bind to receptor molecules in the membrane of the postsynaptic neuron. And by binding to these big molecules in the membrane, they change their shape. And that creates holes in the membrane. These holes allow specific ions to flow in or out of the postsynaptic neuron, and that changes their state of depolarization. Synapses adapt, and that's what most of learning is, changing the effectiveness of a synapse. They can adapt by varying the number of vesicles that get released when a spike arrives, or by varying the number of receptor molecules that are sensitive to the released transmitter molecules. Synapses are very slow compared with computer memory, but they have a lot of advantages over the random access memory on a computer. They're very small and very low power, and they can adapt. That's the most important property. They use locally available signals to change their strengths, and that's how we learn to perform complicated computations. The issue, of course, is how do they decide how to change their strength? What are the rules for how they should adapt? So, all on one slide, this is how the brain works. Each neuron receives inputs from other neurons. A few of the neurons receive inputs from the receptors. It's a large number of neurons, but only a small fraction of them. And the neurons communicate with each other in the cortex by sending these spikes of activity. The effect of an input line on a neuron is controlled by synaptic weight, which can be positive or negative. And these synaptic weights adapt. And by adapting these weights, the whole network learns to perform different kinds of computation. For example, recognizing objects, understanding language, making plans, controlling the movements of your body. You have about 10 to the 11 neurons, each of which has about 10 to the 4 weights. So you probably have 10 to the 15, or maybe only 10 to the 14, synaptic weights. And a huge number of these weights, quite a large fraction of them, can affect the ongoing computation in a very small fraction of a second, in a few milliseconds. That's much better bandwidth to stored knowledge than even a modern workstation has. One final point about the brain is that the cortex is modular, or at least it learns to be modular. Different bits of the cortex end up doing different things. Genetically, the inputs from the senses go to different bits of the cortex, and that determines a lot about what they end up doing. If you damage the brain of an adult, local damage to the brain causes specific effects. Damage to one place might cause you to lose your ability to understand language. Damage to another place might cause you to lose your ability to recognize objects. We know a lot about how functions are located in the brain, because when you use a part of the brain for doing something, it requires energy, and so it demands more blood flow, and you can see the blood flow in a brain scanner. So that allows you to see which bits of the brain you're using for particular tasks. But the remarkable thing about cortex is it looks pretty much the same all over. And that strongly suggests that it's got a fairly flexible universal learning algorithm in it. That's also suggested by the fact that if you damage the brain early on, functions will relocate to other parts of the brain. So it's not genetically predetermined, at least not directly, which part of the brain will perform which function. There's convincing experiments on baby ferrets that show that if you cut off the input to the auditory cortex that comes from the ears and instead reroute the visual input to auditory cortex, then the auditory cortex that was destined to deal with sounds will actually learn to deal with visual input and create neurons that look very like the neurons in the visual system. This suggests the cortex is made of general purpose stuff that has the ability to turn into special purpose hardware for particular tasks in response to experience. And that gives you a nice combination of rapid parallel computation once you've learned, plus flexibility, so you can learn new functions. So you're learning to do the parallel computation. It's quite like an FPGA, where you build some standard parallel hardware, and then after it's built, you put in information that tells it what particular parallel computation to do. Conventional computers get their flexibility by having a stored sequential program, but this requires very fast central processors to access the lines in the sequential program and perform long sequential computations. In this video, I'm going to describe some relatively simple models of neurons. I'll describe a number of different models, starting with simple linear and threshold neurons, and then describing slightly more complicated models. These are much simpler than real neurons, but they're still complicated enough to allow us to make neural nets that do some very interesting kinds of machine learning. In order to understand anything complicated, we have to idealize it. That is, we have to make simplifications that allow us to get a handle on how it might work. With atoms, for example, we simplify them as behaving like little solar systems. Idealization removes the complicated details that are not essential for understanding the main principles. It allows us to apply mathematics and to make analogies to other familiar systems. And once we understand the basic principles, it's easy to add complexity and make the model more faithful to reality. Of course, we have to be careful when we idealize something not to remove the thing that's giving it its main properties. It's often worth understanding models that are known to be wrong, as long as we don't forget they're wrong. So, for example, a lot of work on neural networks uses neurons that communicate real values rather than discrete spikes of activity. And we know cortical neurons don't behave like that, but it's still worth understanding systems like that. And in practice, they can be very useful for machine learning. The first kind of neuron I want to tell you about is the simplest. It's a linear neuron. It's simple. It's computationally limited in what it can do. It may allow us to get insights into more complicated neurons, but it may be somewhat misleading. So in a linear neuron, the output y is a function of a bias of the neuron, b, and the sum over all its incoming connections of the activity on an input line times the weight on that line. That's the synaptic weight on the input line. And if we plot that as a curve, then if we plot on the x-axis the bias plus the weighted activities on the input lines, we get a straight line that goes through 0. Very different from linear neurons are binary threshold neurons that were introduced by McCulloch and Pitts. They actually influenced von Neumann when he was thinking about how to design a universal computer. In a binary threshold neuron, you first compute a weighted sum of the inputs, and then you send out a spike of activity if that weighted sum exceeds the threshold. McCulloch and Pitts thought that the spikes were like the truth values of propositions. So each neuron is combining the truth values it gets from other neurons to produce a truth value of its own, And that's like combining some propositions to compute the truth value of another proposition. At the time, in the 1940s, logic was the main paradigm for how the mind might work. Since then, people thinking about how the brain computes have become much more interested in the idea that the brain is combining lots of different sources of unreliable evidence, and so logic isn't such a good paradigm for what the brain's up to. For a binary threshold neuron, you can think of its input-output function as if the weighted input is above the threshold, it gives an output of 1, otherwise it gives an output of 0. There are actually two equivalent ways to write the equations for a binary threshold neuron. We can say that the total input z is just the activities on the input lines times the weights, and then the output y is 1 if that z is above the threshold, and 0 otherwise. Alternatively, we could say that the total input includes a bias term, so the total input is what comes in on the input lines times the weights, plus this bias term, and then we can say the output is 1 if that total input is above 0 and is 0 otherwise. And the equivalence is simply that the threshold in the first formulation is equal to the negative of the bias in the second formulation. A kind of neuron that combines the properties of both linear neurons and binary threshold neurons is a rectified linear neuron. It first computes a linear weighted sum of its inputs, but then it gives an output that's a non-linear function of this weighted sum. So we compute z in the same way as before. If z is below 0, we give an output of 0. Otherwise, we give an output that's equal to z. So above 0 it's linear, and at 0 it makes a hard decision. So the input-output curve looks like this. It's definitely not linear, but above 0 it is linear. So with a neuron like this, we can get a lot of the nice properties of linear systems when it's above 0. We can also get the ability to make decisions at 0. The neurons that we'll use a lot in this course, and are probably the commonest kinds of neurons to use in artificial neural nets, are sigmoid neurons. They give a real valued output that is a smooth and bounded function of their total input. It's typical to use the logistic function, where the total input is computed as before, as a bias plus what comes in on the input lines weighted. The output for a logistic neuron is 1 over 1 plus e to the minus the total input. If you think about that, if the total input's big and positive, e to the minus a big positive number is 0, and so the output will be 1. If the total input's big and negative, e to the minus a big negative number is a large number, and so the output will be 0. So the input-output function looks like this. When the total input is 0, e to the minus 0 is 1, so the output's a half. And the nice thing about a sigmoid is it has smooth derivatives. The derivatives change continuously, and so they're nicely behaved, and they make it easy to do learning, as we'll see in lecture 3. Finally, the stochastic binary neurons. They use just the same equations as logistic units. They compute their total input the same way, and they use the logistic function to compute a real value, which is the probability that they will output a spike. But then instead of outputting that probability as a real number, they actually make a probabilistic decision, and so what they actually output is either a 1 or a 0. They're intrinsically random. So they're treating the p as the probability of producing a 1, not as a real number. Of course, if the input is very big and positive, they will almost always produce a 1. And if the input's big and negative, they'll almost always produce a 0. We can do a similar trick with rectified linear units. We can say that the output, this real value that comes out of a rectified linear unit if its input is above 0, is the rate of producing spikes. So that's deterministic. But once we've figured out this rate of producing spikes, the actual times at which spikes are produced is a random process. It's a Poisson process. So the rectified linear unit determines the rate, but intrinsic randomness in the unit determines when the spikes are actually produced. In this video, I'm going to show you an example of machine learning. It's a very simple kind of neural net, and it's going to be learning to recognize digits. And you're going to be able to see how the weights evolve as we run a very simple learning algorithm. So we're going to look at a very simple learning algorithm for training a very simple network to recognize handwritten shapes. The network only has two layers of neurons. It's got input neurons, whose activities represent the intensities of pixels, and output neurons, whose activities represent the classes. What we'd like is that when we show it a particular shape, the output neuron for that shape gets active. If a pixel is active, what it does is it votes for particular shapes, namely the shapes that contain that pixel. Each inked pixel can vote for several shapes, and the votes can have different intensities. The shape that gets the most vote wins, so we're assuming there's competition between the output units. That's something I haven't explained yet, and we'll explain in a later lecture. So first we need to decide how to display the weights. And it seems natural to write the weights on the connection between an input unit and an output unit, but we'd never be able to see what was going on if we did that. We need a display in which we can see the values of thousands of weights. So the idea is for each output unit, we make a little map, and in that map, we show the strength of the connection coming from each input pixel in the location of that input pixel. And we show the strengths of the connections by using black and white blobs, whose area represents the magnitude, and whose color represents the sign. So the initial weights that you see there are just small random weights. Now what we're going to do is show that network some data and get it to learn weights that are better than the random weights. The way we're going to learn is when we show it an image, we're going to increment the weights from the active pixels in the image to the correct class. If we just did that, the weights could only get bigger, and eventually every class would get huge input whenever we showed it an image. So we need some way of keeping the weights under control, and what we're going to do is we're also going to decrement the weights from the active pixels to whatever class the network guesses. So we're really training it to do the right thing rather than the thing it currently has a tendency to do. If, of course, it does the right thing, then the increments we make in the first step of the learning rule will exactly cancel the decrements, and so nothing will change, which is what we want. So those are the initial weights. Now we're going to show it a few hundred training examples, and then look at the weights again. And so now the weights have changed. They've started to form regular patterns, and we show it a few more hundred examples, and the weights have changed some more, and a few more hundred examples, and a few more hundred examples, and a few more hundred, and now the weights are pretty much at their final values. I'll talk more in future lectures about the precise details of the learning algorithm, but what you can see is the weights now look like little templates for the shapes. If you look at the weights going into the 1 unit, for example, they look like a little template for identifying ones. They're not quite templates. If you look at the weights going into the 9 unit, they don't have any positive weights below the halfway line. That's because for telling the difference between 9s and 7s, the weights below the halfway line aren't much use. You have to tell the difference by deciding whether there's a loop at the top or a horizontal bar at the top. And so those output units are focused on that discrimination. One thing about this learning algorithm is, because the network's so simple, it's unable to learn a very good way of discriminating shapes. The what it learns is equivalent to having a little template for each shape, and then deciding the winner based on which shape has the template that overlaps most with the ink. The problem is that the ways in which handwritten digits vary are much too complicated to be captured by simple template matches of whole shapes. You have to model the allowable variations of a digit by first extracting features and then looking at the arrangements of those features. So here's examples we've seen already, and if you look at those 2s in the green box, you can see there's no template that will fit all those well and will fail to fit that 3 in the red box well. So the task simply can't be solved by a simple network like that. The network did the best it could, but it can't solve this problem. In this video, I'm going to talk about 3 different types of machine learning: supervised learning, reinforcement learning, and unsupervised learning. Broadly speaking, the first half of the course will be about supervised learning. The second half of the course will be mainly about unsupervised learning, and reinforcement learning will not be covered in the course because we can't cover everything. Learning can be divided into 3 broad groups of algorithms. In supervised learning, you're trying to predict an output when given an input vector. So it's fairly clear what the point of supervised learning is. In reinforcement learning, you're trying to select actions or sequences of actions to maximize the rewards you get, and the rewards may only occur occasionally. In unsupervised learning, you're trying to discover a good internal representation of the input, and we'll come later to what that might mean. Supervised learning itself comes in 2 different flavors. In regression, the target output is a real number or a whole vector of real numbers, such as the price of a stock in 6 months' time, or the temperature at noon tomorrow. And the aim is to get as close as you can to the correct real number. In classification, the target output is a class label. The simplest case is a choice between 1 and 0, between positive and negative cases, but obviously we can have multiple alternative labels, as when we're classifying handwritten digits. Supervised learning works by initially selecting a model class, that is, a whole set of models that we're prepared to consider as candidates. You can think of a model class as a function that takes an input vector and some parameters and gives you an output y. So a model class is simply a way of mapping an input to an output using some numerical parameters w, and then we adjust these numerical parameters to make the mapping fit the supervised training data. What we mean by fit is minimizing a discrepancy between the target output on each training case and the actual output produced by our machine learning system. And an obvious measure of that discrepancy, if we're using real values as outputs, is the squared difference between the output from our system, y, and the correct output, t, and we put in that half so it cancels the 2 when we differentiate. For classification, you could use that measure, but there's other more sensible measures which we'll come to later, and these more sensible measures typically work better as well. In reinforcement learning, the output's an action or sequence of actions, and you have to decide on those actions based on occasional rewards. The goal in selecting each action is to maximize the expected sum of the future rewards, and we typically use a discount factor so that you don't have to look too far in the future. We say that rewards far in the future don't count for as much as rewards that you get fairly quickly. Reinforcement learning is difficult. It's difficult because the rewards are typically delayed, so it's hard to know exactly which action was the wrong one in a long sequence of actions. It's also difficult because a scalar reward, especially one that only occurs occasionally, does not supply much information on which to base the changes in parameters. So typically, you can't learn millions of parameters using reinforcement learning, whereas supervised learning and unsupervised learning, you can. Typically in reinforcement learning, you're trying to learn dozens of parameters, or maybe 1,000 parameters, but not millions. In this course, we can't cover everything, and so we're not going to cover reinforcement learning, even though it's an important topic. Unsupervised learning is going to be covered in the second half of the course. For about 40 years, the machine learning community basically ignored unsupervised learning except for one very limited form called clustering. In fact, they used definitions of machine learning that excluded it. So they defined machine learning in some textbooks as mapping from inputs to outputs. And many researchers thought that clustering was the only form of unsupervised learning. One reason for this is that it's hard to say what the aim of unsupervised learning is. One major aim is to create an internal representation of the input that is useful for subsequent supervised or reinforcement learning. And the reason we might want to do that in two stages is we don't want to use, for example, the payoffs from reinforcement learning in order to set the parameters for our visual system. So you can compute the distance to a surface by using the disparity between the images you get in your two eyes. But you don't want to learn to do that computation of distance by repeatedly stubbing your toe and adjusting the parameters in your visual system every time you stub your toe. That would involve stubbing your toe a very large number of times, and there's much better ways to learn to fuse two images, based purely on the information in the inputs. Other goals for unsupervised learning are to provide compact, low-dimensional representations of the input. So high-dimensional inputs, like images, typically live on or near a low-dimensional manifold, or several such manifolds in the case of the handwritten digits. What that means is, even if you have 1 million pixels, there aren't really 1 million degrees of freedom in what can happen. There may only be a few hundred degrees of freedom in what can happen. So what we want to do is move from 1 million pixels to a representation of those few hundred degrees of freedom, which would be equivalent to saying where we are on a manifold. Also, we need to know which manifold we're on. A very limited form of this is principal components analysis, which is linear. It assumes that there's one manifold, and the manifold is a plane in the high-dimensional space. Another definition of unsupervised learning, or another goal for unsupervised learning, is to provide an economical representation for the input in terms of learned features. If, for example, we can represent the input in terms of binary features, that's typically economical because it only takes one bit to say the state of a binary feature. Alternatively, we could use a large number of real-valued features, but insist that for each input, almost all of those features are exactly 0. In that case, for each input, we only need to represent a few real numbers, and that's economical. As I mentioned before, another definition of unsupervised learning, or another goal for unsupervised learning, is to find clusters in the input. And clustering could be viewed as a very sparse code. That is, we have one feature per cluster, and we insist that all of the features except one are 0, and that one feature has a value of 1. So clustering is really just an extreme case of finding sparse features.